In the previous video, we reconstructed the secret using Lagrange interpolation. But now we're going to look at it also from a different point of view and see that you can also recover the secret or reconstruct it using, like, from a linear algebra point of view, like solving a linear system. So suppose we want to interpolate a polynomial of degree at most t minus 1. And so, of course, we can write that as f of x equal to a0 plus a1x plus a2x squared all the way to a t minus 1 x to the t minus 1, right? And so the unknowns for us are these coefficients here. And if we know t points, what that means is that we know these. So think of it like this. We know t points means that we know x1, f of x1, we know x2, f of x2, we know xt, f of x t, right? So that means that each point, if we replace this, so let me write it down here. If we do f of x1, if we know it, we know that that's equal to a0 plus a1 x1 plus a2 x1 squared plus a t minus 1 x1 t to the minus 1. So we know that it's written like this, and so that gives us one equation. And if you write f of x2, you have another equation, and so on. So you can write it as this linear system here, right? So go review your linear algebra notes. So you can write this as this linear system over here. So if you multiply, so for example, if you multiply the first row by this column, you get exactly this equation here. You get a0 plus a1x1 plus a2x1 squared all the way to a t minus 1 x1 to the t minus 1 equal to f of x1. If you multiply the second row here by this column, you get the second equation you would get here, right? So that means that essentially what's happening is you're trying to determine these a's and you have a linear system for them. Now, this matrix here is a very special matrix. It's called a Vandermonde matrix. So it's matrices where the xi's are, let's say, distinct, and they're just powers. Like it goes like 1, x1 squared, all the way to x1, t minus 1. Then it goes 1, x2 squared, and so on. And what can be shown about the Vandermonde matrix is that if it is invertible, if and only if all the points are distinct. And then when that happens, of course, if this matrix is invertible, if you invert it and multiply by both on the left by both sides, you can actually solve this and you're going to get a unique solution. Now, why is the Vandermonde matrix invertible? Well, the determinant of the Vandermonde matrix, you can show that this determinant is going to be equal to the product of the differences of the entries that you put of the xi's. And so since this product contains only one factor for every pair, the determinant is going to be non-zero exactly when no two of them are equal. So in other words, remember that if the determinant is non-zero, then the matrix is invertible. So the matrix is invertible exactly when all the points x1 to xt are distinct. And so this is why in Shamir secret sharing, we give the participants shares at distinct non-zero points, right? So if two people receive that at the same point, they would not give us two independent equations, and so we would not be able to solve the system. But if the points are distinct, then any t shares gives an invertible system, and therefore they determine the polynomial uniquely. And so this is the linear algebra reason of how Shamir secret sharing works in terms of the reconstruction. So let's return to the same example as before that we already solved with polynomial interpolation. So our polynomial was this f of x, our secret was here, and we had these two random coefficients. And these were the shares that were given to each one of the participants. So f1, so teller 1 got f of 1, teller 2 got this, teller 3 got this, and teller 4 got this. And we're thinking about it in terms of them seeing equations and wanting to solve in order to reconstruct S. And so before we showed how to do that with polynomial interpolation, we showed that how to get the formula for participants 1, 2, and 3 to be able to reconstruct the secret. Now we're going to show how to do it via a linear system. So if you take participants 1, 2, and 3, the linear system that you're going to get, so it's these three equations, and this can be written as f of 1, f of 2, f of 3 equal to 1, 1, 1, 1, 2, 4, 1, 3, 4, S, R1, R2. And so the whole point is that if this matrix is invertible, which it is because it's a van der Waals matrix with different values 1, 2, and 3, you can multiply this by the inverse on the left, and it's going to give you an equation to obtain S. And so that's exactly what we do, right? So this is just rewriting that. Oh yeah, so this is just rewriting the equation we saw. Now, you can invert this, go see your linear algebra notes. Just remember, and this is very important, that we are in Z5. So that means that when you're doing operations, you need to, when you're doing your Gaussian elimination, you need to remember that you're dividing in Z5. So if you need to divide by 2, you need to find the inverse of 2 in Z5 and multiply by that, and so on. So do everything in Z5. You can compute the inverse of this matrix. In Z5, it's going to be this matrix over here. And from this, you can obtain, you just want to obtain the secret. You can actually decode the random stuff, but you don't need it, and at least not for this application. And so if you want the secret here, it's just going to be this first row times this column. So you're going to be 3f1 plus 2f2 plus f3. And this is exactly the same thing that we had found with the polynomial interpolation.